Hello! And welcome! What if I told you that everything you think you know about reality is wrong? That the solid world around us, the chair you're sitting on, even your own body, is governed by a set of rules so bizarre, so counterintuitive, that they sound like something from a science fiction novel. This isn't fiction. This is the world of quantum mechanics. I'm Brian Cox, and today we're going on a journey to the very edge of reality to explore the fundamental principles of the quantum universe. Quantum physics is the science of the very, very small. It's the theory that describes the building blocks of our universe. Atoms, the electrons that orbit them, the photons of light, and a whole zoo of other subatomic particles. Now, you might think that small things should just behave like smaller versions of big things, like tiny billiard balls bouncing around, but they don't. Down at this fundamental level, the universe plays by an entirely different set of rules. Rules that challenge our common sense and force us to rethink the nature of existence itself. One of the first and most profound mysteries we encounter is something called wave-particle duality. Imagine a particle like an electron. You'd picture it as a tiny, solid dot, right? And a wave, like a ripple on a pond, is a spread-out disturbance. They seem like complete opposites. But in the quantum world, things like electrons and photons can be both. They can behave like a concentrated particle in one moment and a spread-out wave in the next. What's even stranger is that which one they choose to be seems to depend on us, on whether we're looking. This leads us to one of the most famous experiments in all of physics. The double-slit experiment. It's elegant in its simplicity, but staggering in its implications. Imagine firing tiny particles, say, electrons, one by one, at a screen with two narrow slits in it. Behind this screen is a detector that records where each electron lands. If electrons were just tiny balls, you'd expect to see two distinct lines on the detector, corresponding to the two slits. Simple. But that's not what happens. When we don't watch which slit the electrons go through, they create a pattern of many lines, an interference pattern. This is the hallmark of waves interfering with each other. As if each single electron went through both slits at once, as a wave, and then interfered with itself. But here's where it gets truly mind-bending. If we place a detector at the slits, to see which one each electron goes through, the interference pattern vanishes. Suddenly, we see just the two lines we originally expected. The very act of observing, of measuring which path the particle took, forces it to choose to be a particle and behave like a tiny ball. It's as if the universe knows we're watching and changes its behavior accordingly. The observer isn't just a passive spectator. We are participants in the creation of reality. This strange behavior is explained by another core principle, superposition. Before we make a measurement, a quantum particle doesn't have a definite position or a definite state. Instead, it exists in a cloud of possibilities, a superposition of all its potential states at once. The electron isn't here or there. It's in a probabilistic combination of everywhere it could be. It's only when we interact with it, when we measure it, that this wave of possibilities collapses into a single, definite reality. So, before you look, the electron really does go through both slits simultaneously. The moment you look, it's forced to be in one place. Now, if that hasn't stretched your brain enough, let's talk about what Albert Einstein called spooky action at a distance. This is the phenomenon of quantum entanglement. You can create two particles, say two photons, that are intrinsically linked. Their properties are correlated in a special way. Let's say one has a property we'll call spin, which can be either up or down. If they're entangled and you measure one particle and find its spin is up, you will instantly know, with absolute certainty, that the other particle's spin is down, no matter how far apart they are. Whether they're in the same lab or on opposite sides of the galaxy, the connection is instantaneous. It's as if they are one single system, defying our classical notions of space and separation. This isn't just a theory. It's been tested and confirmed over and over again. It's a deep and mysterious connection woven into the fabric of the cosmos. The role of observation in all of this is perhaps the most debated and philosophically charged aspect of quantum mechanics. How can the act of looking at something change what it is? Does reality only become concrete when a conscious mind observes it? These questions have puzzled physicists and philosophers for a century. There are many interpretations, from the idea that consciousness itself collapses the wave function to the many worlds interpretation, which suggests that every possible outcome of a quantum measurement actually happens, each in its own parallel universe. The universe splits. So, in one universe, the electron went through the left slits, and in another, it went through the right. We just happen to be in one of them! While we don't have the final answer, it's clear that quantum theory forces us to confront the relationship between the observer and the observed in a way that classical physics never did. We might be thinking this is all just abstract, theoretical stuff that only happens in a lab. But the truth is, you're using quantum mechanics right now. The device you're watching this on, whether it's a phone, a tablet, or a computer, relies on semiconductors. The behavior of electrons in those silicon chips is purely quantum. Without understanding the quantum nature of materials, we couldn't have designed the transistors that power our entire digital world. Lasers, from the ones in Blu-ray players to those used in surgery, operate on the principle of electrons jumping between quantum energy levels. GPS navigation has to account for relativistic effects, but the atomic clocks it relies on are quantum devices. Even nuclear power and MRI scanners in hospitals are applications of our knowledge of the quantum world. This strange, ghostly theory is the bedrock of modern technology. But beyond the technology, the philosophical implications are profound. For centuries, science was built on a deterministic worldview, pioneered by Newton. The idea was that if you knew the position and momentum of every particle in the universe, you could, in principle, predict the entire future. The universe was like a giant clockwork machine. Quantum mechanics shattered that view. At its heart, it is a theory of probabilities, not certainties. We can never predict with 100% accuracy where a single electron will land. We can only calculate the probability of it landing in different places. This suggests that randomness might be a fundamental feature of the universe, that the future is not written in stone. It challenges our very concepts of cause and effect, reality, and what it means to know something. And the journey is far from over. The frontiers of quantum research are pushing into even more exciting territory. You've probably heard of quantum computing. A classical computer uses bits, which are either a 0 or a 1. A quantum computer uses qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. And thanks to entanglement, qubits can be linked. This allows quantum computers to perform a vast number of calculations simultaneously. For certain problems, like designing new molecules for medicine or breaking modern encryption, they could be exponentially more powerful than any supercomputer we could ever build. We're still in the early days, but the potential to revolutionize science, medicine, and artificial intelligence is immense. So, from wave particle, duality, to spooky entanglement, quantum physics reveals a universe that is fundamentally weird, probabilistic, and interconnected in ways we're only just beginning to understand. It shows us that the reality we perceive with our senses is just a sliver of what's truly out there. It's a world built not on solid certainties, but on a shimmering dance of possibilities. It's a reminder that the universe is not only stranger than we imagine, it is stranger than we can imagine. And for a scientist, and I hope for you too, that is the most beautiful and exciting thought of all. Thank you for joining me on this journey into the quantum realm. If you enjoyed this exploration, please consider liking this video and subscribing for more adventures into the cosmos. See you next time.